But one issue that's very important is that it's Little's law, which wasn't used in high-performance computing because in the way we think about it today, it certainly didn't exist in 1961. The number of threads must equal the parallelism times the latency. So if your delays, your communication delays are longer, you need more threads to hide it. And if you increase the number of parallelism on the, that's available, you also have to increase the number of threads. What's interesting is that P and lambda are both growing with time. We expect for a few years anyway that the number of cores per chip will double every 18 months. That will probably slow down unless technology is able to resolve certain outstanding problems. And lambda is also increasing with time for the reason I described earlier. The delay off the chip is growing relative to the speed of the processor, that is in toto, the whole chip. And so these are things we have to cope with. In particular, we have to handle more and more threads over time. The problem is it's difficult to implement the hiding of latency, that is communication delays. For example, if we look at a parallel program here and think of the green areas as when the computation occurs and the red areas when communication occurs, there are large portions of the running time that are not doing anything productive if we think of what's productive as being computation. Here's a program in which the darker areas signify we're overlapping the two activities and runs in less time. There are two reasons why it's difficult to tolerate communication delays. One is that we have to write what are called split phase algorithms. You initiate communication here or data motion, then you compute and you wait. Now for those of you that are more familiar with traditional computers, you have this idea of prefetching. If you know that, for example, a load of a word of memory takes so long, then what you can do is you can actually go ahead and issue a prefetch instruction which says, I'm going to want this memory in a little while, and I can afford to wait because I'll do something else. I'll compute some least squares problem or something that I have already in memory. The other issue is that we have to actually partition. I'm going to show how this all works out very shortly to arrange so we can actually distinguish things that can run now from what can be run later, and we have to then schedule them appropriately. That distracts focus from the domain science. This is why only a few of us actually do this today. This is a very hard technique to implement. It only makes everything that we have to do in parallel processing much harder. The other issue is, of course, that the implementation details become entangled with the logic of the program. What you do to write the correct program, that is a numerically correct program, becomes mixed up and indistinguishable from the parts that actually deal with these performance issues. And latency tolerance is ubiquitous across using hybrid systems, multi-core systems that have accelerators. It is not going to go away. I will show it in the context of writing an MPI program. But the same ideas, perhaps a slightly different form, also apply to using these new technologies. Hence, this is a technique for coping with technological change. Okay, the motivating application is a very simple one, but it's a good one. We'll solve Laplace's equation in 3 dimensions with Dirichlet boundary conditions, recognizing this is not the best way to solve Poisson's equation, but we'll tolerate it because it might be a building block, or it is a building block, for example, in more advanced methods like multigrid, which rely on this as an essential kernel. So you have to deal with this particular application to deal with multigrid. Okay. Here's the iteration below. It's a very simple one. I haven't shown all the code, but of course that's the meat of the loop where the work is done. And the classic implementation of a parallel computer is to essentially use domain decomposition. We split the problem up into pieces, and we can see that in each internal piece we have boundary conditions. In this case, though, these are external boundary conditions, but the areas that are in between the partitions are internal boundary conditions. They arise because of the reordering, the way that we've done the computation on a parallel computer. One thing to think about on a parallel computer, I always like to think about it this way, is a parallel computer simply says that if you can do something in an arbitrary order, then it's a parallel computation. That is, I can sweep the values left to right, up or down, by diagonals or at random, as long as I do each one once, exactly once in each iteration. So you can see then this is a parallel computation. We could simulate a parallel computer by simply using a serial computer to do these in an arbitrary order. And we know the Jacobi's method has no dependencies in the loop because there's a separate left-hand side which is updated completely before we go to the next iteration. So that means we're free to arbitrarily order these computations. And what happens then is we exchange data in this purple region here, called a ghost region or a halo region, periodically after every iteration to ensure that we have the correct boundary conditions. What this does is, in terms of the program behavior, is create a pattern where everybody communicates at about the same amount of time and starting at about the same time, and similarly for the computation. So it's a phase calculation, goes back and forth, called bulk synchronous parallelism. There may be small differences which I've exaggerated here so you can see them because of slightly different variations in the running of the processors, the time it takes the data to go through the communication network to the other processor, over a shared bus, say, on Tesla to get to the different processors and so on. We wouldn't do it this way on Tesla, but this is illustrating the idea of the data motion that has to occur in order to run this problem. Right? Oh, and to remind you, if you use Tesla, for instance, you would send a piece of the problem over to the Tesla machine if you had a very large problem, because the memory is limited to a few gigabytes and you might have some enormous problem. And so you'll somehow have to move a piece, solve it, and put it back to enable the next piece to run. Right? Remembering that memory per core is still limited, and you have to think about this limitation in terms of the speed of the processor. If you have a fast processor, you need more memory to keep it fed. If you don't, then you have to go off processor and get more data, which takes time. And the Tesla processor could be tens of times faster than your conventional algorithm, and that means it needs a lot more memory. So if you think about a machine which has maybe 1 or 2 gigabytes per core, it's really more towards 2 gigabytes per core. If the Tesla processor is even 10 times faster, you need to have 10 times as much memory. So a gigabyte of memory, or even 3 or 4, on the Tesla device itself is not really a lot of memory to have, given how fast it is. And it's important to think about that when coping with technological change. Your amount of memory is always going to be limited, even though it may seem large in absolute terms. In terms of its speed of the device that's computing on it, that's not a lot of memory, really. Okay, so we've established the need to move data. And then there's another way to actually do this that'll avoid the need to wait so long on the communication, and that is as follows. We recognize that, in fact, the interior of that problem, the green plus the red, has a distinction in the following sense. The purple data are the off-processor data that have to arrive before we can solve the problem. But only the red data depend on those. Right? The stencil is very small. It only reaches out one point in all directions, so that we can actually begin to compute on the green data before the red data. Change the ordering. Remember, it's a parallel computation. We're allowed to do this. We can change the ordering, and we create an additional inner halo region so that we now excuse me, sweep over the green region while we're waiting for the red data to arrive. So we make a distinction between these two kinds of data. Then, when we're done computing, we wait to see if we're done, and if we are, we're ready to compute. And now you can see the runtime involves these darkened areas with only short delays, maybe very, very small, for the data motion. Okay? Here are some early results in my research group back in the, starting in the late 90s, on an old, no longer existing IBM SP3 system with Power 3 processors, with a system called KELP2, in which we recovered 2/3 of the communication wait time. And since the communication wait time was about 20 or 22% of the total running time, the program sped up by 14%. Okay? In a sense, you could say we're a little bit ahead of our time because communication delays were not that severe then, but we knew they were coming, and here they are now, 13 years later, or 11 years later, rather. Other applications, we got up to 28% on the summa matrix multiply algorithm. And so that actually is a significant improvement. Makes a large difference. Today, because of the change in the rate of speed at which processors communicate and compute, the communication is relatively slower nowadays. The communication delays are expected to be larger as well. Okay. Now, there's a small problem here in that the variant we use to overlap imposes a total ordering. In particular, we have to communicate all the red data before we can do any of the green data.